Pressure. Learning objectives. Pressure and its main characteristics. Use of pressure in daily life. Pressure in solids, liquids and gases. Measuring atmospheric pressure. When a force acts on an object, pressure is produced. In other words, pressure is the force acting on a unit area of the object. In everyday life, we use the term pressure such as tire pressure, air pressure, blood pressure, water pressure and so on. So first let us define pressure. What is pressure? Pressure. Pressure is the normal force, i.e. perpendicular, which is acting on unit area. It is represented by P. Pressure. P equals normal force upon area on which force acts equals F upon A. The SI unit of pressure is N/m2, a scalar quantity known as a Pascal and written as Pa. We know that when we pull a spring, or press our hands against a wall or stand on the ground, then we are applying a force. A push or a pull means a force. Whereas, force is important, the more important is the area over which it acts. This leads us to define a quantity called pressure. Thus, it is the force divided by the area on which it acts, i.e. the force, F, per unit area, A, at any point determines the pressure at that point. Activity 12.1. Take a rectangular block, weighing 100 N. The area of the block when placed on ground from its broader side is 0.1 square meters, whereas it is 0.01 square meters when placed on the ground from its narrow side. Let us see the pressure exerted by this block on the ground. We saw that the pressure did not take only the weight of the block into account but more importantly, the area which came under that pressure. Pressure equals 10,000 Pascal, Pa. Main characteristics of pressure. The above experiment proves that 1. Pressure is a scalar quantity, i.e. has magnitude but no direction. 2. The area on which the pressure is exerted is more important. 3. The more the area, the lesser the pressure. 4. The lesser the area, the more the pressure. 5. Pressure at all points at equal depth is equal. Example 1. A block weighing 1500 N rests on an area of 5 square meters. Calculate the pressure exerted by the block on the surface which supports it. Solution. We know that P equals Fa. Here, F equals 1500 N and A equals 5 square meters. What we don't know is the P. Thus, applying the formula we have P equals F upon A, or P 1500 N upon 5 meters into 2 equals 1500 upon 5 equals 300 Pa or Nm-2. Example 2. A cubical block of mass 2 kg with each side of 2 cm is lying on the ground. Calculate the pressure exerted by the block on the ground. Take G equals 9.8 milliseconds minus 2. Solution. The mass of the block, M equals 2 kg. Weight, F, of the block, mg equals 2 kg times 9.8 cm minus 2 equals 19.6 N. Side of the cube, A, equals 2 cm equals 2 upon 100. M equals 0.02 meters. Area of the lower surface of the cube A equals a minus 2 equals 0.02 multiply 0.02 equals 4 multiply 10 minus 4 m into 2. Using P equals F upon A equals P equals 19.6 N upon 4 multiply 10 minus 4 M into 2 equals 4.9 multiply 10 into 4 Nm minus 2 equals 49,000 Pa. A cubical block. Use of pressure in daily life. The following are the uses of pressure in our daily life. The railway tracks are laid on large-size sleepers so that the thrust, force, due to weight of train is spread over large area to reduce the pressure on the railway line. It is comfortable to carry a load on shoulders because the shoulders provide larger area, thus reducing the pressure on the body. Tractors have large tires so that they present large area to reduce the pressure due to the weight of the tractor on the soft soil. Camel is much heavier than man, still camel walks more swiftly in sand than man because the wide feet of camel present large area, thus reducing the pressure, and so the camel does not sink in the sand. A sharp knife is more effective in cutting the objects than a blunt knife because blunt knife has thick edge which puts the force of our hand to a larger area reducing the pressure, whereas sharp edge presents less area for the pressure to develop and cut the object effectively. A needle has a pointed sharp tip and a blunt large head. The head presents a large area putting less pressure on the finger or thumb, whereas the same needle presents very less area at its sharp tip to develop more pressure so that the needle pierces the object. Tanks, bulldozers, and other heavy mechanical equipment are fitted with the caterpillar tracks which consist of large flat surfaces punctured with short spikes. If the equipment was supported by the spikes only, the pressure would be enormous due to small area of contact. And that would make the equipment to sink only a little way into the supporting surface. The players in a football or cricket game wear the shoes which have spikes on their soles. These spikes provide less area of contact, exerting more of the body weight on the ground so that the player does not fall and remains firm even while running. Spacecraft which landed on Moon and other planets had all been fitted with large area pads on their feet to prevent them sinking too far into the unknown surfaces. Sci facts. It is important to realize that the pressure at a point in the liquid is dependent only on the vertical depth of the point. So, more the depth, more the pressure of the liquid. Stress and strain. The pressure exerted on a surface is sometimes known as a stress and it results in strain. If the supporting surface is not strong enough to withstand this strain, it may bend or break. Example: a man wishes to cross a water body through a plank as the bridge. The wooden plank is thin and the man knows that the plank cannot bear his weight and may break, drowning him into the water. What he does is that he lays flat on the plank and moves slowly along its surface. He reaches safely to the other side. However, the plank is slightly bent in the center. How does it happen? In case he would have stopped over the plank, his feet would have covered small area, exerting more pressure of his body on the plank. By prostrating over the plank, he provided large area to his body pressure to exert on the plank. Thus less area more pressure and more area less pressure applied and he crossed the gap safely. People's crossing a river through a plank. Pressure in solids, liquids and gases. Pressure in solids. Pressure exerted by a solid on a supporting surface can be explained in terms of molecular interaction between the molecules of the two substances involved. The weight of the solid is responsible for the solid exerting a force equal to its weight on the surface. Pressure in liquids. Pressure in liquids is different from that in both solids and gases. In liquid, the forces holding the molecules together are not strong enough to give the liquid a definite shape like solids. Liquids are therefore to be held in containers and they take the shape of the container. The surfaces of the container exerts a force on the liquid. This force is equal or higher to the opposite force exerted by the fluid on the containing surface. The force exerted by the liquid is called thrust and it is perpendicular to the surface. Activity 12.2. At the deeper point in a liquid, the pressure is greater. Fill a tall cylinder with 3 equal fixed outlets 1, 2 and 3 with tap water. Position 3 beakers 1, 2 and 3 to catch the water from the 3 outlets. Open up the mouths of the outlets when the tap is on in the cylinder. You will observe that the water from the outlet 3 is thrust further horizontally than that from outlet 2, which in turn goes further than that of outlet 1. This shows that the pressure is greater at the deeper point in the liquid. The volume of water collected from the jets, outlets, also increases with the depth of the outlet. Activity 12.3. Liquids exert same pressure in all directions at a particular depth. Consider a section of liquid of cross-sectional area A, depth h and weight W with its upper surface subject to atmospheric pressure P0 and the lower surface to pressure P. There must be no unbalanced vertical force acting on it, so that the section of liquid remains in equilibrium. Thus F0 plus W equals F. The thrust of the liquid is a force equal to its weight W equals mg equals V rho g, where rho equals density, V equals volume of the liquid. Since the volume 5 is h times A, it follows that W equals ha rho g. The forces P, A on the equal areas A at each end face of the section of liquid must be equal and opposite. Liquids are incompressible, but will flow and hence occupy the space available. They exert a pressure equally in all the directions, hence occupy the space available. Activity 12.4. Pressure varies with the density of liquid. Take a glass tube with both ends open. Tie a rubber balloon on the lower end of the tube when it is placed upright, vertical. Add the tube with plain water up to mark A. Observe the budge in the rubber balloon which will expand due to water pressure. Now take another tube of the same capacity and tie a balloon to one end of it as done before. Now fill the tube with salt solution up to the same mark A. Observe the bulge in the balloon. It will be more than the first balloon. The difference in the size of the budge is because of the difference in the density of the liquids that exerts pressure on the balloon. Pressure in a liquid is independent of the cross-sectional area and therefore the shape of the vessel, container, if the pressure at the surface of liquid is atmospheric pressure. Pressure in gases. The atmosphere is the best laboratory to know about the pressure gases exert. But before atmospheric pressure is studied, let us see how gases exert pressure. Gas exerts a pressure on the walls of its container by molecular bombardment. Activity 12.5. Pressure due to Earth's atmosphere. When a gas molecule approaches very close to the walls of the container, the molecules of the container repel the approaching molecules of gas, changing their momentum. From the Newton's third law of motion it follows that the exerting molecules must exert an equal and opposite force on the wall of the container. Very large number of molecules traveling at relatively high speeds are involved, so the force exerted can be very high. Thus the molecular bombardment of the walls of the container exerts quite considerable pressure. Activity 12.6. Consider a metal can, A, open to the atmosphere. The atmospheric pressure will be the same inside and outside the can because its mouth is open. Now replace the screw cap on the mouth of the can, B, so that the air inside the can is sealed from the atmosphere. The pressure inside the can is still atmospheric, but it is not due to the weight of the column of the air above it. The pressure now present inside the closed can is due to the bombardment of molecules on its walls by the trapped air, which is less than atmospheric pressure. Activity 12.7. Strength of the atmospheric pressure. Boil some water in a tin can keeping its mouth open. The steam produced will replace the air normally in the can and the molecules of the air will exert the pressure equal to the atmospheric pressure because the mouth is open. Now remove the can from the heat and seal its mouth by screwing the lid and quickly cool it by pouring cold water over it. The can suddenly crumples. Why? Because the steam inside the can has condensed into a very small volume of water, leaving a partial vacuum behind. The number of molecules per unit volume is now reduced. Since temperature inside the can is reduced, so the molecules will move slowly, which cannot now exert much pressure on the walls of the can. This pressure being very low cannot equalize the atmospheric pressure exerting from the outside of the can. The difference in the pressures makes the can to crumple, suggesting the strength of the atmospheric pressure. Activity 12.8. Sucking inside a straw. How do we sip juices through a straw? Of course, by sucking out the air inside the straw. The external atmospheric pressure acting on the sucker forces the sucker against the flat surface. The pressure P into 2 of the air that remains in the straw is less than the atmospheric pressure P0. Therefore, the liquid is forced up the straw into the mouth of the person who sucks at the straw. The pressure P into 1 of the bottom of the sucker is greater than the atmospheric pressure P into 0. Measuring atmospheric pressure. On the surface of the Earth, the atmospheric pressure is maximum at the sea level. But, as we go up in the atmosphere from the surface of Earth, the atmospheric pressure goes on decreasing. It is clear that the atmospheric pressure on the top of a high mountain will be much less than at its base. The atmospheric pressure is measured by a simple barometer. A simple barometer can be made using a thick-walled tube, 1 meter long, which is sealed at one end. Mercury is carefully poured into the tube. This mercury-filled tube is inverted into a mercury reservoir. The atmospheric pressure on the surface of Earth, at the sea level, is 760 millimeters of mercury. Working. Since the pressure exerted by the column of mercury in the full length of the tube is greater than the atmospheric pressure P0, some mercury will run out of the tube into the reservoir, leaving a vacuum in the mercury will run out of the tube into the reservoir, leaving a vacuum in the tube with no pressure in it. The mercury will stop flowing once the pressure at the lowest horizontal level is the same both inside and outside the tube. This is the atmospheric pressure to be read on the meter rule attached to the instrument. Standard atmosphere, ATM, is a unit of pressure defined as 1,01,320 Pascal. Pressure is often quoted in height, or head of a column of liquid, which is roughly 0.76 meters of mercury. Some uses of atmospheric pressure. Lift pumps. The ordinary lift pump raises water from a well or spring because of atmospheric pressure. The weight of atmosphere pushes down against the water in the well and forces it up the pipe. Siphons. Atmospheric pressure makes it possible to move water or other liquids by using siphon from higher level to a lower level, when it is inconvenient to pour the liquid from one container into another. Atomizer. The ordinary atomizer works because of atmospheric pressure. The pressure in a moving liquid is the least where the liquid is flowing most rapidly. It also holds true for gases. Some interesting facts. Balloon bursts when too much air is blown into it. The balloon becomes the container and the molecules of air in it bombard its walls. Since more air is drawn into the balloon, there is an imbalance of pressure. Pressure inside the balloon being more than the atmospheric pressure outside. The walls of the balloon fail to withstand the inner pressure and the balloon bursts. Inverted containers resist dipping into liquids. When a container, say a glass bottle or a pitcher, is pushed into water with its mouth touching the surface of water, the water column exerts pressure which is repelled by the pressure within the container. Since the pressure exerted by water column is greater than the pressure inside the container, it pushes the container away, resisting its dip into the water. Keywords. Pascal. The SI unit of pressure, denoted as bar. Stress. Pressure exerted on a surface. Strain. Result of the stress. Thrust. Pressure applied by liquids, gases and solids. Containers. Vessels containing liquids and gases. Siphon. A type of tube. Summary. Pressure is the normal force acting on a unit area. Smaller the area, larger the pressure. Larger the area, smaller the pressure. Pressure plays an important role in our daily life. Sharp knife cuts easily because it has smaller area on cutting edge. Railway tracks are laid on large-sized sleepers to provide more area. Spacecraft tests landing on Moon have large area pads fitted, so that it does not sink on unknown surfaces. Camel walks fast in sand due to its broad feet, which provide larger area to the pressure exerted by camel's body. Pressure exerted by solids on a supporting area has molecular interaction. Pressure in liquids at a point is dependent only on the vertical depth of the point. Liquids exert some pressure in all directions at a particular depth. Pressure varies with the density of liquid. Pressure in a liquid is independent of the cross-sectional area. Atmosphere is the best laboratory to learn about the pressure in gases. Gas exerts a pressure on the walls of its container by molecular bombardment. Atmospheric pressure is measured by barometer with the help of mercury. Lift pumps, siphons and atomizers use atmospheric pressure for their functioning. Pressure is represented by P equals F, A where F is force and A is area.